Good day, everyone. I am Charles Aimiwu Osaiti, a PhD candidate of the Department of Electrical and Computer Engineering, Faculty of Engineering and Applied Sciences, Memorial University. I will be making a presentation on an open source Internet of Things based SCADA system for remote oil and gas facilities using Node-RED and Arduino microcontrollers. The work will consider the deployment of Internet of Things-based devices for remote monitoring, supervision, and control of a low flow rate oil well. The work will be organized by introduction, followed by the challenges and the problems identified. The case study in question will be explained, and the system modeling will be done. It will comprise hardware and software integration. Security concerns will also be considered, and the work will be concluded and recommendations made for future work. Scada is an acronym for Supervisory Control and Data Acquisition. It is a family of technology which entails supervising, monitoring, and controlling both field and industrial processes. Typically, sensors are deployed which monitor the condition of specific elements of the process being monitored, and the results of those sensors are sent to central controllers, and the parameters of interest monitored and adjusted to the desired level. There are several generations of SCADA. The generation we'll be considering in this work is the fourth generation of SCADA. Considering SCADA generally usually consists of devices deployed to monitor the processes in the field, and the input of this the conditions of the parameters is then relayed to a, a microcontrollers which collect and aggregate the data together, and the data is then sent through wired or wireless means to a central master terminal unit, which um, serves as a human machine interface to um, monitor the value of the parameter of interest and initiate intervention, either human control or set points. And so all the generation of SCADA have that general architecture of collection of data from the field and aggregation of the data, logging and processing, and transmission and visualization. The generation of SCADA will be considered in this work is the fourth generation of SCADA, which deploys Internet of Things devices are distributed in the process being monitored, usually over a large area. The data collected by these sensors are aggregated by remote terminal units and relayed to a master terminal unit for processing, visualization, and monitoring. The IoT technology will be applied to remote monitoring and control of a pump referred to as a donkey head pump or a sucker rod pump, or so-called beam pump. It consists of a donkey head or a nodding pump which helps to convert the rotating energy of from an electric motor to vertical rectilinear motion in the subsurface. And there are several parameters of interest in this um, case study. The temperature of the fluid, the flow rate of the fluid, the position of the donkey head, the speed of the electric motor, the level of the produced fluid, the pressure and temperature of the produced fluids. So there are several parameters that will be monitored in this work. Attempts have been made in literature to reproduce the behavior of the pump in the lab. Some attempts have been made to produce a miniaturized 3D model of the pump. This work aims to examine the communication between the sensors that will be deployed in such models and simulate the behavior in terms of the interaction of information gathering, collection, and transmission for the IoT devices that will be deployed on an actual 3D model. As can be seen from the slide, the primary energy um, drives the electric motor, which can be solar energy or connected to the grid. When the motor receives the electrical energy, it converts it to mechanical energy, which is then in turn converted by the donkey head mechanism to a rectilinear up and down motion, which translates into pumping action downhole. The produced fluid, which is usually a mixture of oil, water, and gas, is then produced into separator tank, which helps to separate and segregate the oil, water, and gas. As can be understood, the production in the upstream sector is a high-stake business, and the possibility of, because of the changing parameters and the unique environment, the possibility of pollution, the possibility of explosion, and the possibility of hazards and risks that exist are, are very, very clear. The dynamic nature of such upstream production implies that health and safety is of the highest priority. And this implies that data need to be collected to monitor the balance and the behavior of such a system to prevent explosion and accidents to either personnel working on the facility or those living in the neighboring vicinity. Environmental pollution is also a major concern since spills, fires, and explosions can happen as a result of overflow of fluids or leakages. Production is also a very important factor because profitability is a big consideration, and hence there needs to be a monitoring of the produced fluid in terms of the flow rate and the level, and even the temperature of the fluid to ensure that the production is both sustainable and profitable. Reservoir monitoring, also monitoring of the well and well monitoring, also require that these parameters are closely monitored. The integrity of the well in terms of the continuity, the ability of the well to continue producing at the expected level is also very important. And pressure and flow and temperature monitoring are also very important for maintaining well integrity. There's also a need for sake of planning and planning and the long-term profitability of the well, and monitoring of production will only be possible when data, production data, and well data are available for the well and logged and available on a continuous basis. On the long term, the ability to intervene in terms of asset management, asset integrity, and well management to ensure that the pressure of the well and the pressure of the reservoir are maintained appropriately to ensure that the production is made sustainable for as long as possible is also very important. And hence, dynamic optimization requires that data is collected in real time, and historical data is also used to plan future well maintenance. The case study that we'll be considering is a low flow rate oil well, which is driven by an electric motor. The electric motor in question will be powered by a solar power generator. So after conversion of the light energy to DC or direct current power, that energy is then converted to alternating current by inverter, and then to uh, alternating current to drive the electric motor. As was previously explained, that when the energy from the rotary energy is then converted to rectilinear energy and translate into um, pumping action downhole. In the course of the operation of a sucker rod pump, several parameters are important to produce what is called a dynamometer, which gives an indication of the efficiency of production, comparing the rod load and the rod position. So by monitoring the inclination of the working beam and the position of the rod and load on the rod, and comparing it with the amount of energy, the current and the voltage used to drive the electric motor, and the flow rate of the produced fluid and the level of produced fluids, the condition of the producing well and the efficiency of the producing well can be estimated. And hence, the parameters such as inclination, rod load and rod position, flow rate, and the level of fluid in the tank, and the voltage and current of the power used to drive the prime mover are very important, because when correlated, they can be used to tell a good picture of the production efficiency, and also for early diagnosis of fluid production problems, fluid pound, gas lock, or sand production, which can help, if arrested on time, help to reduce the cost of maintenance and reduce the chance of failure. In this work, the design methodology would be to use a system approach. We have three subsystems: the master terminal unit, the subsystem 1, and subsystem 2. Subsystem 1 will be the Arduino microcontroller 1, while subsystem 2 will be the Arduino microcontroller 2. The sensors are all connected to their respective terminal units. The voltage sensor, current sensor, rotary encoder, accelerometer, distance sensor, and the electric motor load are all connected to the Arduino Mega terminal unit microcontroller, while the temperature sensor, the flow rate sensor, the level sensor, and the liquid crystal display are connected to the Arduino Uno. Both terminal units are then connected to a master terminal unit, which is the local server and which can be remotely accessed over the internet. The desire to have two microcontrollers is, number one, the um, to reduce the chance of failure of a single microcontroller, which could result in a catastrophic consequences for the system. And hence, redundancy is one of the reasons to increase the reliability. The second is to also um, ensure that we are able to deploy two means of communication for each of the terminal units. The Arduino Mega will be adopting Fermata protocol for accessing the sensor data, while the Arduino Uno will be using purely serial communication. Both micro terminal units will be connected to the master terminal unit using a USB connection. The assumption is that all the terminal units are available on site, and the server is also available on site and remotely accessible remotely over the internet. In terms of operation, the Arduino Mega controls the voltage, current, rotary encoder, accelerometer, distance sensor, and the electric motor. It communicates with the sensors using Fermata protocol, and the voltage and current are the values of the power supply, which is the solar panel connected to the Arduino Mega, while the rotary encoder determines the position of the electric motor connected to the that drives the rod pump. The accelerometer determines the inclination of the rod pump, and the distance sensor determines the position of the rod. The electric motor is the prime mover that drives the rod pump. They are all connected to the Arduino Mega via Fermata protocol, and the data is related to the master terminal unit. The Arduino Uno connects the temperature sensor, the flow sensor, and the level sensor to the master terminal unit, while the liquid crystal display serves as the on-site display. The master terminal unit is connected to the outside world through the internet, and it's available online. The analog sensors connected to the Mega measure and collect the parameters of interest and convey it to the Arduino Mega. The Arduino Mega also reads the sensor values from the voltage sensor and the distance sensor and calculates it via Fermata. and relays the data to the master terminal unit. The Arduino Uno collects the temperature and flow rate values and reads the fluid level on the LCD through the I2C bus. The Arduino Uno then displays the values of the temperature and flow uh, through serial communication to the LCD screen and also to the master terminal unit. The Arduino Uno connects to the master terminal unit via serial communication and also connects to the um, local IoT server. The Arduino Uno client receives the data um, and sends it via serial communication. The master terminal unit receives the data and logs and displays it. So it logs the data, it aggregates it, and displays it for analysis and visualization. Fermata protocol is adopted in the Arduino Mega as a protocol for communication between the master terminal unit and the Arduino. Now, since the Mega carries a very large number of sensors and has to read and execute logic on a very large number of sensors, we decided to use the Fermata protocol to ease the computational logic of reading from the sensors. And so, standard Fermata is the Fermata firmware that we downloaded from the Arduino IDE onto the host computer. And through the Fermata protocol, we're able to access the pins, the respective pins that are used to read and control the sensors that are connected to the Arduino Mega. The advantage of this is that it shifts the computational complexity from the Arduino device, from the Arduino Mega device to the host master terminal unit, and which is able to read and change the state and condition of the pins seamlessly. And hence we're able to execute the desired operation easier on the with the firmware running on the master terminal units. And so the Arduino IDE provides a Fermata library called Standard Fermata, which allows us to access all the general purpose input and output pins from the master terminal unit. Hence, we change the state to change the mode and we can read from directly from the MTU without shifting the complexity to the Arduino Mega. We're able to access and control all the Arduino pins, the input and output pins from the software on the host computer without uploading the sketches anytime we make any changes. For the Arduino Uno, all the computations are done in the Arduino Sketch. So from the Arduino IDE, we're able to program the logic of reading each of the sensors from the Arduino IDE. We run and compile the sketch, and the outputs or the results of the sketch are then relayed to the host MCU. So there's a difference. Unlike the Arduino Mega, where the computations are done on the directly on the MTU, for the Arduino Uno, computations are done on the Arduino sketch itself, and then the results relate to the MTU. A web-based programming tool called Node-RED helps us to represent the flow of data between the interconnected devices on a web browser interface. And hence, we're able to interconnect the devices by means of flows. So by creating functions, we're able to connect the input from each sensor to a function and produce or demonstrate the output from that function. So we're able to display the outputs from the MTU as both bars, as gauges and charts. And so we're able to obtain bars or gauges and charts for the voltage, current, and position sensor for the Arduino Mega, and for the flow rate level sensor, and temperature sensor for the Arduino Uno. As you can see, the fact that fermata protocol is used in the Mega indicates that a flow is created for each individual sensor because they are read separately. While for the Arduino Uno, they are read separately and related directly to the output separately. While for the Arduino Uno, you can see that all the data is processed within the Arduino IDE and then transferred from the COM port to the MTU. At the MTU, they are now separated into the individual output. So the fact that fermata is used in the Mega can be seen in the fact that each individual sensor input produces its own independent sensor output, whereas in the Arduino Uno, all the sensor outputs are processed in a single sketch and then passed or separated into their individual outputs through serial communication. The remaining sensors that are served by the Arduino Mega are the accelerometer, the distance sensor, which is sharp infrared sensor, and the electric motor, which is like a transducer. So the accelerometer, the accelerometer used here is a three-axis accelerometer, and it measures the position basically of the device in the X, Y, and Z direction, and can also be used to determine the inclination depending on the respective values of these parameters. The each of each value from each the value from each axis is taken through a function, and all the value from each of the axes are combined into a single output which is displayed in a chart. So because it is on a two-dimensional plane, the values are pretty straightforward and stable. The distance sensor also gives the position of the, the infrared device, and it's displayed in a chart and a gauge. And so we can see depending on the position of the device, the distance is shown in a chart and as a gauge. The electric motor is being turned and on and off by the Arduino Mega through the matter protocol. So each of those sensors are the pins of each of these sensors are assessed. They are the state, they are turned on and off, and they are controlled via the fermata protocol running on the host MTU. Since the Node-RED application is a web-based programming tool, it is produced by integration of the input from the IoT sensors and the Node.js runtime. Since Node-RED is running on the web server, it is only available on that local server, and hence it's for access to Node-RED to be possible from the outside world. We use a concept called port forwarding. Now, since the service of Node-RED is running on the whole server, when a request is made, normally when a request is made by a client to access the service of Node-RED running on the web server, a router is used. Now, since the Node-RED service is running on the server, for us to open up the access to the Node-RED server, we allocate or assign a port to the Node-RED server, to the Node-RED running on the web server. And so when the client requests are made to the to Node-RED, it is the public IP address of the router that is accessed. And so that public IP address is resolved when the client request is made. The request is resolved to the public IP address of the router. After resolving to the public IP address, the router now maps the ports that the client has required, maps the port to the private IP address of Node-RED. So we in this work we isolated the IP address of the host computer. We isolated it from the IP address of the router. This is to ensure that access is controlled and the IP address is secure. So using a firewall device called a NAT router, the the port that Node-RED is open on is is transferred from the router IP address to the private IP address of Node-RED, and responses like to the client request are also transferred from the web server to the router and back to the client. And so we can see that the private or host server is isolated or separated from the client request and is not visible to the client. Why this is done is to ensure security and protection. As can be seen from the previous slide, when a client makes a request of Node-RED application, the Node-RED application listens on a specified port for traffic for that port. And so when the request is made and the 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 port is mapped from the public IP address of the router to the private IP address of the device for the specific port of interest, we use a reverse proxy server called Nginx. In this work, we use Nginx, we place Nginx in front of our web server for authentication to ensure that a username and the password is requested from, from a client when the request is made. This is to ensure that access is controlled and authentication is requested every time a client tries to make a request for access to the Node-RED graphic user interface and the Node-RED dashboard running on the web server. And hence, we bind the Node-RED to a particular port, and before that port running on the web server is accessed, a username and a password is required from the client before access is granted. The goal of this work has been to deploy an Internet of Things based open source SCADA architecture for remotely controlling an oil and gas facility. We have so far been able to demonstrate that using our system architecture of one master terminal unit and two remote terminal units, which are two Arduinos, we've been able to remotely read the values of the voltage and current of the power supply, the fluid level, the temperature, the distance. We've also been able to read the rotary position and the flow rate and accelerometer values. Going forward, our goal is to integrate the sensor values and, and calibrate the readings obtained from these sensor values in an actual model, and then begin to use the integrated readings obtained from the sensors for effective decision making. Now, we chose the soccer rod pump because of its very high level of deployment for onshore wells. And the work so far still has a lot of improvement. Namely, number one, we need to improve the security of the Node application by deploying secure socket layer SSL to encrypt the connection to the Node application, so that from HTTP we can encrypt to HTTPS to make the Node application more secure in terms of connection. Number two is to ensure that we want to make the Node application cloud native. It means we will build it on IBM Watson and deploy it to take advantage of the robust provisions of the cloud architecture. We also intend to use the rotary encoder not only as a monitoring device but as a control device to ensure that we can use it to control the direction of the electric motor prime mover and also the speed, so that in addition to using the Arduino Mega for start and stop, we can have a more robust control over the um, operation of the electric motor, and hence over the flow rates. By varying the speed of the motor, we can vary the flow rate of production of the well, and also um, help in case of um, making interventions to the well or flow control. Lastly, we intend to, using the sensors mounted on the 3D model, we intend to obtain the values of the sensors and then use it to calibrate a Simulink and Simscape model of the entire system. So after mounting the sensors on an actual 3D model in the lab, we intend to build a Simulink and Simscape model of the solar powers generating system and a dynamic model of soccer rod pump. By integrating these models together and feeding it with the data obtained from the sensors in the 3D model, we hope to calibrate the 3D model. We hope to use the 3D model to calibrate the Simulink model and hence obtain hopefully a digital twin that can be used to predict the behavior of the 3D model itself, predict its failure, and using a data-driven approach, plan and diagnose problems that are encountered in production. Here are a few references of both completed and ongoing work in the field of deployment um, of IoT Scada for um, pumping solutions and also in terms of producing a digital soccer rod pump. Thank you.